I am Pawan Sharma, coming with third module in solution. In last lecture, we discussed vapor pressure of solution containing volatile components. Today we will discuss colligative properties. Colligative properties. What is the meaning of this colligative properties? You have to understand first. Colligative properties are those properties which are directly depends on particles of solute. One important thing here, these particles should be non-volatile. Particles should be non-volatile. One another important thing, these non-volatile solute, they do not undergo association, no association, and no dissociation. Or you can say, in colligative properties, we will take non-volatile solute which do not undergo association and dissociation. First, we will discuss four such kind of the volatile solutes. Or you can say, we are to take non-electrolytes. Non-electrolytes means where there is no dissociation or association. Or you can say, we are to take examples of carbohydrates, that may be glucose, sucrose, or you can say urea, having formulas. Such kind of the substance we are to take in first phase. Or you can say, after this colligative, we will discuss for electrolytes, where dissociation and association. For that, we will take another concept, that is Ventov factor. First, we will consider non-electrolytes. I think it is clear to you what is colligative properties. Colligative properties means which depends on particles of solute, and particles should be non-volatile and where there is no association or no dissociation. These are four types. Colligative properties are of four types. I am taking one by one. First colligative property is relative lowering of vapor pressure. Relative lowering of vapor pressure. Second one, that is elevation in boiling point. Third one is depression in freezing point. Fourth one is osmotic pressure. These four colligative properties we are to discuss. So I take first colligative properties, that is relative lowering of vapor pressure. Relative lowering of vapor pressure. Relative lowering of vapor pressure. Another name of this is, that is Raoult's law. for solution, Raoult's law for solution containing non-volatile solute, or you can say here we are taking solution, or we are discussing vapor pressure for solution. In solution, you know, two components, solvent and solute. Solvent, and solvent is denoted by A, and this we are taking because both components we can't have non-volatile. Reason behind, because both can't show vapor pressure, because non-volatile do not show any vapor pressure. So that is why we are to take solvent A, that is volatile. Or you can say you are to take liquid. Solute, that is denoted by B, or you can say it is non-volatile. Or you can say you are taking solute. Keep in mind. We can understand like this. Here, we take a container. In this container, we take solvent, or you can say take liquid, or we are taking solvent, or that is denoted by A. These are the molecules of A. Or you can say it is pure now. Now what happens? These molecules vaporize and show vapor pressure, and for this vapor pressure denoted by P naught A, that is vapor pressure of pure state, P naught A. Now if we add B, what is that? That is solute, and this solute is non-volatile. If we add this into this, what happens? Then solution will be formed. Like this. Now this is solution. Where both components A and B are present. Or you can say non-volatile solute is added to volatile liquid. Now here both particles present, A as well as B. Now what happens? When liquid is pure, all the molecules from the surface come up and forms the vapors and show vapor pressure, that is denoted by P naught. Now if we add non-volatile solute, in non-volatile, what happens? Only A particles or only solvent particles vaporize. These solute particles, they do not vaporize. Reason, because they are non-volatile. In such case, vapor pressure only shown by A, not shown by B, or PB, or you can say vapor pressure for this is 0. Or you can say vapor pressure of solution, PS. It means vapor pressure of solution. You know that is PA plus PB. Now PB is non-volatile. It doesn't show any vapor pressure. So you can say vapor pressure of solution, that is equal to vapor pressure of pure solvent, P. Or you can say when solvent is pure, the then vapor pressure, suppose vapor pressure is 400 nanometer, 400 nanometer suppose. Now then we add non-volatile solute. Now solution is formed. Now here both components are present on the surface, solute as well as solvent, but only solvent molecules will vaporize, solute molecules can't vaporize. Or you can say there is less force surface area for vaporization, or less vapors will be formed. Or you can say vapor pressure will be decreased because less vapors are formed, less will be the vapor pressure. Or you can say when it is pure 400 nanometer, then right now it won't be 400 nanometer because less vapors are formed here, because less surface area for solvent to vaporize. Or you can say vapor pressure goes on decrease. Or you can say vapor pressure of pure solvent P naught A, that will be more than the vapor pressure of a solution. In other words, you can say on addition of a non-volatile solute into pure liquid, vapor pressure of solvent goes on decrease. From here you can see P naught A PS. For better understanding, we take one question from here, which show more vapor pressure. This is the question, which show more vapor pressure. First case I am taking 1 molar glucose solution, 0.2 molar glucose solution. I am taking 2 molar glucose solution, and you are to tell which has more vapor pressure. Now here we have discussed by addition of non-volatile solute, vapor pressure goes on decrease. More the non-volatile quantity of more non-volatile solute is added, more vapor pressure will be decreased. Here quantity here 1 molar, here 0.2, and here 2 molar. Here non-volatile solute is more, here least. We can say here vapor pressure is least, and here 0. Quantity is less of non-volatile solute, here vapor pressure is more. So right answer is this one. Or we can conclude here vapor pressure is inverse with quantity of concentration of solute, quantity of solute. If we add more quantity of solute, then less will be the vapor pressure. I think it is clear to you. Now take here, we know vapor pressure of solution, that is sum of vapor pressure of two component, solvent as well as solute. And solvent is volatile, it show vapor pressure. Solute is non-volatile, so it do not show vapor pressure, or you can say it has a zero vapor pressure. So we can say PS is equal to PA. And from last lecture we have discussed Raoult's law. And Raoult's law, what is that? that is P naught A XA. We know PB equal to P naught B XB. This is Raoult's law. Now here we can put PA equal to P naught A XA. So we can write here PS equal to P naught A XA. I am putting the value of PA. PA can be written as P naught A XA. In last lecture we have already discussed Raoult's law. Raoult's law, what is that? Vapor pressure of each component in solution that depend upon its mole fraction. You can say product of these two, pure state vapor pressure and its mole fraction. Here we can, this equation is 1. This equation is 1. Now here PS equal, bring here P naught A. Here this is XC. This equation is second. Now you subtract these two quantities from 1 both sides. 1 minus PS upon P naught A. Here 1 minus XC. 1 minus XC. Come to this side. Take LCM here. Take LCM. P naught A. So it will be P naught A minus PS. And 1 minus XA. What is that? We know XA mole fraction of a solution means solvent mole fraction plus solute mole fraction, that is equal to 1. So we can write XB is equal to 1 minus XA, or you can say in place of 1 minus XA we can write here XB. XB. This is our property, colligative property, that is relative lowering of vapor pressure. Understand here. P naught A. P naught A means vapor pressure of pure state. And this is PS, vapor pressure of solution. It means solvent vapor pressure is more than that of solution, because it is subtracting here. Or you can say on addition of non-volatile solute into pure liquid, vapor pressure goes on decrease. Or you can say this quantity is called lowering in vapor pressure. Lowering in vapor pressure. Lowering in vapor pressure. And this complete, this is divided, this is, or you can say in relation, this lowering in comparison of pure solvent. So this term is called relative lowering of vapor pressure. And this is directly dependent upon what? What is it? This is mole fraction of, mole fraction means mole ratio, mole fraction of solute. Students, what is colligative? Already we have, what is colligative properties? Colligative properties means which are that depend upon the particles of solute, or you can say it is the mole fraction of solute. So we can say this is a colligative properties. This is a colligative properties. Come here. P naught E minus PS upon P naught E. Okay, and here this is XB, or this is XB. What is this? It is the mole fraction of solute. How you can calculate mole fraction of any component? Number of moles of that component divided by में total number of moles. Total number of moles. For dilute solution, we are taking dilute solution, or you can say here number of moles of solvent is very large than number of moles of solute, dilute में. Or you can say B can be neglected in the place of Na. So we can write XB is equal to NB upon Na. That is why we can write P naught A minus PS upon P naught A equal to, we put here X in place of this, NB upon Na. Or also you can understand from here, this relative lowering of vapor pressure that depend upon what? Number of moles of solute particles. That is why it is a colligative property. And also you know NB, what is it? This is the number of moles of solute. That can be written as given mass upon molar mass. These are the notation. Mass of solute upon molar mass of solute. Like this, we can write Na is equal to given mass of solvent upon molar mass of solvent. Putting the value of this Nb, that is Wb upon Mb, Na that is Wa upon Na. Also, this is the formula comes out. Final result from this relative lowering of vapor pressure, that comes out to be P naught A minus PS upon P naught A, that is equal to Wb upon Mb, here that is Wa into Ma. This formula is for dilute solution. Generally, in our syllabus, we take dilute solution. But if concentrated solution is given for competitive exams, some questions can be asked. So this formula can be modified. Only difference is P naught A minus PS upon PS. That is Wb upon Mb, here Wa into Ma. Or you can say this formula can be applicable for both dilute solution as well as concentrated solution. For dilute solution, for both kind of problem can be solved from this formula. But generally in our NCRT book, all numericals are done by this formula. That is why we will use it. Now I would like to clear what are these terms, and then after we will take one numericals on it. P naught A, you know what is it? P naught A, that is vapor pressure of pure solvent. PS, that is vapor pressure of solution. Students, one thing you have to mind, solution also you can say solvent. Same thing. Also this can be written as PA as well, because in non-volatile solution containing only vapor pressure due to solvent. Wb, you know, that is mass of solute, mass of solute. Ma, this is molar mass of solvent, molar mass of solvent. Mb, that is molar mass of solute, molar mass of solute, mass of solute. And Wa, that is mass of solvent, mass of solvent. And you know A notation for solvent, B notation for solute. For better understanding, one numerical is needed. That is why first we solve one numerical problem. Numerical. Find mass of non-volatile solute, non-volatile solute. This is numerical from board. Find mass of non-volatile solute. Molar mass of this is given 40 gram per mole. I am writing here 40 gram per mole. 40 gram per mole. Find mass of non-volatile solute having molar mass is 40 gram per mole is dissolving is dissolving 114 gram octane to lower its vapor pressure to 80%. 80%. First, you read this statement very carefully. You are to find mass of non-volatile solute. Non-volatile solute mass, or you can say you are to calculate here WB. 40 gram molar mass. What is given? MB, that is given 40 gram per mole. 40 gram per mole. Dissolved in 114 gram of octane. What is it? This octane is solvent. Octane is solvent. Mass of that is given. WA, that is given. That is 114 gram. This is octane, molar mass of octane. In exam generally it is given. And this is by chance, that is also 114 gram. This will be given in exam. Molar mass, all values. These things are given. Now come to this. Non-volatile solute is dissolved in 114 gram of octane. Octane is, that is liquid, pure liquid, that is volatile or volatile solvent, and you add non-volatile solute. Then what happens? Vapor pressure goes on decrease. Or you can say this 80%. What is this? 80% means it means octane. Suppose this is octane. Here, that is vapor pressure is 100. Now, if we add non-volatile solute, then this solution becomes, and vapor pressure, because addition of non-volatile vapor pressure goes on decrease. This comes to 80%. Or you can say this is P naught A. This is P naught A, or this is PS. You know, vapor pressure of solution is always lower than the pure solution. So these things are given. So what is the formula? P naught A minus PS upon P naught A. equal to WB upon में MB WA into में MB. Putting the value P naught A, that is 100, PS, that is 80, P naught A, that is 100, WB, you are to calculate MA, that is 114, MB, that is 40, WA, that is 140. This cancel with this. And from here, 20 upon 100, that is WB upon 40. So WB will be 40 into 20 upon 100. This comes out to be 8 gram. Your answer will be 8 gram. So this is all about first colligative properties, that is relative loading of vapor pressure. I hope you have understood all the things very easily. Next colligative properties I will take in next lecture. Thank you from my side. Have a